Hello everyone. In this lecture, I want to give you different examples about differentiation rules and how we apply these rules. The first one, it says y equals 5x cubed minus 1 times 2x squared plus 5. Clearly, this is the product of a cubic function and a quadratic function. So product rule is very clear. Y equals u times v. The derivative was u prime v plus v prime u. So that's the formula we are going to use here. So clearly this is u and this is v, and the derivative is going to be u prime, which is the derivative of the first function, that's 15x squared, and we applied the power rule and constant multiple rule to find that derivative. So this is u prime, and then times v, which means times the second function, and then plus the derivative of second, which is v prime, that's going to be 10x here, times the first function, which is 5x cubed. So it's going to be plus 10x times 5x cubed minus 1. Okay, so this is u prime, this is v, and this is v prime, and this is u. So the derivative of u times v is u prime times v plus v prime times u. You can, of course, simplify this by expanding and collecting like terms. That's going to be 30x to the 4 plus 75x squared plus 50x to the 4 minus 10x, which after collecting like terms, it gives you 80x to the 4 plus 75x squared minus 10x. So this is the final answer, simplified answer for the derivative of that product of the two functions. So we did apply the product rule in doing this exercise. We said that we have to recognize the product to begin with, and then you take the derivative of the first function, which is derivative of 5x cubed minus 1, that is 15x squared. You multiply by the second function, 2x squared plus 5, plus the derivative of the second function, which is 4x, 2 times 2, 4x. Why did I write 10x? I don't know. Don't ask me. 2 times 2 is 4x, okay, times the first function. And then you can simplify. So I think the answers are going to change a little bit. This is going to become 20. 4 times 5 is 20. X to the 4, and then minus 4x, okay. So, and then when you collect like terms, you end up with 30 plus 20, which is 50x to the 4, and 75x squared minus 4x, final answer. So this is how it turns out to be. So derivative of the second function was 4x times the first function, okay? And then the rest of it is like algebra and collecting like terms, simplifying and that kind of thing. 15 times 2, 30. And then 15 times 5, 75, x squared. 4 times 5, 20, x to the 4, and then minus 4x. And then the rest of it is just collecting like terms. Next one is a quotient rule kind of exercise. We have to recognize that this is a quotient actually. So we're going to use u over v formula. It's going to be derivative of top, which is 6 times the bottom, and then minus the derivative of the bottom, which is 2x times the top function, all over the denominator squared. So this is the derivative, but we need to simplify it a little bit as much as possible. So 6x squared plus 12 and minus 12x squared plus 2x all over x squared plus 2 all squared. Okay, so negative 2x times 6x and negative 12x squared, and then negative times negative is positive 2x. And now we can collect like terms, negative 6x squared plus 2x plus 12 all over x squared plus 2 in the denominator, all squared. So this is y prime, which is the final answer for the derivative of this rational function. And what we applied here was, of course, the quotient rule. We had u in the top, v in the bottom. So u prime was 6, v was x squared plus 2. We multiplied it. And then minus. Many students, by mistake, they write plus. I have marked thousands of papers. And students, by mistake, sometimes they write plus sign. But you have to be careful. It's minus. Minus v prime, which is the derivative of the bottom, that is 2x. And then times u, which is the numerator 6x minus 1, all over the denominator squared. And the rest of it is just doing multiplication, expanding, simplifying, and that kind of thing. All right. Next exercise, we have a quintic polynomial raised to the exponent of 8. And that reminds me of this combined chain rule with power rule. So what plays the role of u is the quintic function. What plays the role of n is 8, the exponent. So the answer in one shot is going to be 8, which is n right in front, times 5x to the 4 minus 4x cubed minus 2, which is u prime. That's the derivative of inside. And then times u itself. So I rewrite the quintic raised to the exponent of 8 minus 1. Okay, so that is exponent of 7 right there. This becomes the final answer. You see how handy this formula is to apply when you have some polynomial raised to a very high exponent. This next exercise, you may say this is a quotient rule, and I'm not saying no. You can assume the numerator u to be 1, which is a constant, and you can assume v to be this quadratic function in the bottom. However, another way to look at this is to rewrite this with a negative exponent of negative 1, and then we apply the same rule we just applied 2 seconds ago. So we can say the derivative is n times, which is negative 1 times u prime, which is 2x plus 8, and then times u itself, so x squared plus 8x to the exponent of n minus 1. So that's minus 1 minus 1, which is negative 2. So sure enough, this will be negative 2x minus 8 all over x squared plus 8x all squared. We never leave the answers with negative exponents. We always express our answer with positive exponent. Therefore, I wrote this in the denominator, and the negative exponent of 2 becomes positive 2. And this is the final answer. We got it very fast using this formula, which is a combined chain rule with power rule. But of course, first we wrote it in the form of a power. But if somebody wants to apply the quotient rule, assuming that u, the numerator, is a constant, that is 1 in this case, you can also do that. And u prime would be 0, because the derivative of 1 is 0. And then you would just go minus v prime u divided by v squared, which would give you exactly the same answer. But I just wanted to show you another view of doing these questions. This one is a square root function, okay? Y equals square root of 5x squared minus 3. Whenever you want to do these questions, you can apply these shortcut formulas, which are results of actually the same formula. Like if you think about it, you can write this as 5x squared minus 3 to the exponent of 1/2. You can write this square root with a rational exponent, and then you can say n is equal to 1/2 and apply the same formula. For example, you can say y prime equals n, which is 1/2, times 10x, which is u prime, and then times 5x squared minus 3 to the exponent of 1/2 minus 1, which is negative 1/2. And perhaps you can rewrite this in the denominator with a positive exponent. So 10 over 2 is like 5x all over 5x squared minus 3, and express it in radical form is what you get. Now, the thing is that you can use this shortcut formula, and that is not in the textbook, and it's for situations where you want to find the derivative of the square root of a function, okay? In this case, we have square root of 5x squared minus 3. So what plays the role of u is 5x squared minus 3. So u prime is going to be 10x in the numerator, which of course we can write 10x, divided by 2, which is 5x. That's what we got here. and then the denominator is just square root of u, what we had before. So we can, of course, apply this rule, chain rule combined with power rule, to find the answer, but it's longer. It's a faster way, or easier way, or like a shortcut formula that can be used to find the derivative of square root functions. And if it's a cube root scenario, like the mth root of u, it could be like cube root, fourth root, fifth root, sixth root, and so on and so forth. Then you write the derivative of the radicand in the numerator, divided by m times mth root of u to the exponent of m minus 1. So in this case, if I want to apply that formula, it's going to be u prime, which is 2x plus 3, conveniently written in the numerator. M times becomes 3 times mth root of becomes cube root of, because m is 3, and then u is x squared plus 3x minus 1, and we're going to raise it to the exponent of m minus 1, which is 3 minus 1, that is 2. Okay, so this is the final answer that we got in one shot, actually, thanks to this shortcut formula. And this shortcut formula, actually, if you let m equals 2, okay, so the mth root becomes square root, and that becomes like the formula I gave you before. So the first formula is a special case of the second formula, given m equals 2, basically. And if the radicand, which is u in this case, happens to have another exponent, an additional exponent of p, for example, if you have like a cube root or fifth root of something raised to the exponent of another exponent of p, the answer is pu prime over m times mth root of u to the exponent of m minus p. That's the formula, shortcut formula, that gives you the answer in one final shot, in simplified form. Okay, so in the next lectures, I'll try to give you more examples of how we apply these differentiation rules. And meanwhile, you keep practicing, please. Thank you.